Hi everybody, and welcome back to a conversation on the digestive system. This is going to be part 2 of our conversation. Now, where we had left off the last time was sort of running through the parts and pieces of the stomach and sort of what the stomach makes and what the stomach basically does and how the stomach protects itself. And now we're going to run down into the beginnings of the small intestine. But before you can really talk about the beginnings of the small intestine, you have to broach the subject of some of the main accessory organs of the digestive tract, mainly being the pancreas and the liver. And sort of in and amongst this, the gallbladder. So the liver plays a role in producing some materials which the gallbladder then stores. So you can see the liver here would be producing certain products that we'll discuss here in a moment. It will then be stored in the gallbladder, and the gallbladder then has the ability to release these down into the small intestine, along with materials released through this pancreatic duct into said small intestine. Now, as with yesterday, what I will do is I'm going to provide you with a brief overview of sort of how it all works. Then we're going to go into crazy amounts of detail about how it all works. All right, here we go. So your pancreas is sort of, if you grab the stomach and pull it up, you can see it. The pancreas has the texture of like cottage cheese in an old sock or something along those lines. It's really kind of gross in texture. And it has both endocrine and exocrine functions. I put a slide up of this, but I guess not. It has both endocrine and exocrine functions. What this means is it has an endocrine function in the releasing of things like insulin and glucagon to regulate your blood sugar levels, and it has exocrine function. That exocrine function is to release a variety of enzymes, things like amylase, trypsin and lipase, amylase for carbohydrates, specifically starches, trypsin for proteins, lipase for lipids, but, well, I'm not going to say more importantly, but equally as important here is the pancreas's ability to manufacture bicarb. Okay, bicarbonate, or I'll just call bicarb. This is a wonderful agent to augment pH values of a fluid. So, what are the fluids like when they're coming out of the stomach down here? Okay, when they're entering into the small intestine, the fluid in the stomach is incredibly acidic, and the small intestine cannot handle that acidity. So one of the first things that has to happen is the pancreas will release its juices, if you will, that will then contain large amounts of bicarb and will buffer the pH of the chyme entering into the small intestine. So this bicarbonate being there is incredibly important and one of the main protective natures of this pancreas, helping the duodenum or part of the small intestine to function. Then we have the liver and the gallbladder. So the liver is a really big, hardy organ. You can badly damage the liver and it can grow back. It's a big, tough organ. And a liver is quite firm. Like I could take it and knock you off a chair with it. You know, it's a big, hard organ by comparison to the pancreas, which is soft and gushy. And it's made up of individual little subunits called lobules. They're like these weird kind of a round structures, big central veins, and what are called hepatic portal triads on the sides. I'll be showing you those in just a second. But it is made of individual lobules, these little round units. Now, you know a little bit about the liver at this stage. You know that it does indeed help to filter your blood. It certainly does remove some harmful substances, and it does participate in the breakdown of red blood cells. And you realize that in that breakdown of red blood cells, there are some potentially dangerous chemicals. Okay, things like bilirubin, as we'll be discussing here in a second, that must be dealt with in other ways. Now, the liver does indeed pull some materials out of the blood for storage. The liver certainly helps to regulate blood sugar levels by storing glycogen and then breaking that glycogen down when it is necessary to mobilize glucose. For our purposes, the main things I'm concerned with at this stage is that the liver makes bile. Okay, bile contains byproducts of bilirubin, and the idea here is that this bile, as a side effect of red blood cell decomposition, is going to be released down through these hepatic ducts. By the way, anything hepatic is liver, and then stored inside the gallbladder. So the gallbladder is going to store bile. And the reason the gallbladder stores bile is to kind of hold it until you eat foods that are kind of fatty. Fatty foods, you struggle to absorb these without them being what's called emulsified or dissolved into water. Like your body's mostly water, and oil and water don't mix. So you have to have a way of dissolving the oils into fluid, water, so that you can absorb them. That's what bile does for us. Bile is considered an emulsifier. It will surround and bind up these oils and make them available to your system for them breakdown and or absorption. Okay, so it's very important for this. And also, we're going to talk about this a little later, probably when we do the nutrients, but the liver is also responsible in regulating your cholesterol levels by regulating high density lipoproteins and low density lipoproteins. Okay, and let's go here. Oh, by the way, here's a real gallbladder, so this is giving you an idea of the color. It does indeed take on this crazy green appearance. All right, what we have here are some microscope slides. I'm showing you lobules here, these big round units. And the lobule will have a central vein with a hepatic portal triad sort of over in the corner, triad being a hepatic portal vein, a hepatic artery, and a bile duct. Again, bile being this byproduct of red blood cell breakdown. In this, you can see these bile canaliculi. So you have these sinusoidal capillaries, if you will, that are inside of here. And we're going to be breaking down red blood cells, and the byproducts of this, we're going to be absorbing bile through these bile canaliculi and then funneling it through a bile duct and then moving it down into the gallbladder. So you've got a major left hepatic duct and a right hepatic duct. These come together to form what's called a common hepatic duct. Same thing as when we're doing arteries and veins, and that will come down, and normally there's a sphincter down here that closes everything off when you don't have food in the small intestine. So by closing everything off, the liver continuously producing this, it backs up and fills the gallbladder. Okay, so the gallbladder has this cystic duct connecting it here at the common hepatic duct, and they come down to form what's called the common bile duct. You should know this. Okay, you should know the breakdown of how this is structured. I think it's worth your time. They even have the pancreatic duct in there. They're showing you the duodenum in the stomach. It's worth your time. Worth your time. Hepatic portal triads. All right, bile canaliculi. I've sort of already ran you through this. So all of this is just what I said here, that bile is picked up in these very small bile canaliculi and then brought into larger bile ducts and then carried to larger bile ducts and then carried down to be stored in the gallbladder. It's pretty much what I'm saying here. It gives you an idea of what we're dealing with. What I will talk about is it's strangely echoey in the room right now, and it's driving me crazy, folks. So if you see Malfi Rocker, it's because I got a weird echo in here. It's the weirdest thing. Anyway, where am I at? Here. So when you come down here, I said there was a sphincter. That sphincter is a hepatopancreatic sphincter, and it regulates the movement of bile and pancreatic juices into the duodenum. So you can imagine if you haven't eaten anything in a while, there's nothing being moved into your small intestine. There's no reason for you to release pancreatic juice or bile, so you just store it up and wait. And then when you consume foods and you need that material, you can open up that sphincter and allow those chemicals down into the small intestine, into the duodenum, to help you regulate your intake of nutrients. All right, the gallbladder, as seen here, does indeed have a unique green coloration. It does store bile, and in the storage of bile, it also helps to concentrate it. So it's constantly pulling water out of bile, and this can lead to a situation where the bile forms up into solid nodules, and we call those gallstones. Okay, and gallstones are kind of fascinating. I had a student worked at a veterinarian's place and came in with a big cup full of gallstones one day. Craziest thing you've ever seen. Now, the gallbladder does not produce bile. The liver does that. It simply stores it. So the gallbladder is a storage area. And again, bile is a yellowish green fluid. You can see the picture quite clearly here. You can see what the bile looks like. It has that kind of crazy yellowy green color to it. And this is a side effect of the chemicals that it contains. Okay, so what's in bile? Well, a variety of things. So certain minerals, cholesterol, some fats, phospholipids, very importantly here, bile pigments, again, bilirubin from the breakdown of hemoglobin in your red blood cells. And when this material gets put into your small intestine and eventually moves its way into the large intestine, provided it stays in the large intestine for a correct period of time, this bilirubin is going to be broken down into urobilinogen, and this actually gives your feces that kind of brownish color that you think of with feces. Okay, so it's a side effect of the bilirubin being there, and it's breakdown from bacteria that gives feces this kind of brownish color. And I'll be talking more about that here in a second. And also in amongst this, we have bile acids and lecithin. Again, just making the point that your bile is going to be used as an emulsifying agent to help you absorb dietary fat. All right, very important, very important. Oh, worthy of our time is jaundice. So let's talk a little bit about jaundice. You know, who gets jaundice that you think of? People that have major liver issues, or alternatively newborn babies. Let's talk about the newborn baby aspect of this. So a newborn might have a liver which is not yet fully functional, and as a side effect of that, they may not have a liver capable of pulling all this bilirubin out and getting rid of it in appropriate fashion. So this material can actually build up in the tissues and lead to jaundice. Okay, so what we do in this situation is we'll take the kid and put them in ultraviolet light, and the UV light will help to break down these kind of weirdly yellowy green pigments. And then the body can metabolize them more easily and get rid of them. What we're doing is, by giving UV treatment, is we're giving the liver time to get started and do the job that it's supposed to do. So normally, if a kid's born with jaundice, it'll go away pretty quick because the liver's just trying to get started doing what it's supposed to do. This is very common. Jaundice is a side effect of other issues. It's not a disease in and of itself. So jaundice is a side effect of a malfunctioning liver. So you see this in cirrhosis patients as well. Anytime somebody's having major liver issues, jaundice can be a side effect. And then the pancreas. So here is my slide. So what you see here are pancreatic cells and tissues, if you will. All of this is pancreatic, but then you can see these weird light spots. Those are the islets of Langerhans, or the pancreatic islets. And these are the areas that have endocrine function for our purposes. So this is going to be where you make insulin, for example. This is going to be endocrine function. And then all the rest of this is going to be general pancreatic cells that make what's called pancreatic juice. Okay, that is the vast majority of your pancreatic tissues is going to be this exocrine function. So what the heck is pancreatic juice? Well, it's a relatively alkaline mixture. Alkaline, again, slightly basic. We're going to be neutralizing stomach acid. A mixture of water, a whole variety of enzymes. Zymogens, again, these are going to be non-functional enzymes. These are really powerfully catalytic enzymes that can destroy whole cells and tissues. So what we do is we release them in an inactive form, and then we activate them once they're in the gastrointestinal tract, so that they're only interacting with foodstuffs that we've consumed, as opposed to destroying the cells that made them or destroying the linings of your intestinal tract, which we want to prevent. That's why our intestinal tract is just coated in mucus, is to prevent this from happening. Let's see, a lot of sodium bicarbonate, if you will, bicarb, is going to help to balance out that pH as well, so buffering the hydrochloric acid from the stomach. Now, you can see this pancreatic duct running down through here, and what you end up with is a pair of pancreatic ducts. A main pancreatic duct, as you can see here, and then this accessory pancreatic duct. So the idea here is that the main duct is going to go down and connect with the entrance of bile and be controlled by that sphincter, whereas there's also that accessory duct that can allow for small amounts of material to move in without bile also mixing with this. So just a neat little nuance to it. It's kind of a fascinating process. All right, in the pancreas. So what I want to talk about here are these zymogens. Your pancreas releases trypsin and chymotrypsin and carboxypeptidase. All of these are going to be moving in as zymogens and then be activated by activity inside the duodenum itself. So these are going to be made in the pancreas. They're really powerfully catalyzing enzymes. They are really good at breaking down protein. Powerful anti-protein agents as zymogens, released into the lumen of the small intestine and then activated through other enzymatic activity. Okay, so then when activated, they just tear through the proteins that you've been consuming. There are also a variety of other pancreatic enzymes released via pancreatic juices. These are things like pancreatic amylase, which is a very powerful anti-starch enzyme, pancreatic lipase, which is a very powerful lipid breakdown enzyme, and ribonuclease and deoxyribonuclease, which obviously break down DNA and RNA. All right, so the pancreas produces all of these. It produces most of the enzymes that will break down the foodstuffs that you consume. So all of the major foodstuffs you consume, there will be enzymes produced to break those down by the pancreas. So the pancreas is a very important role for your digestive system, not just blood sugar regulation. The pancreas does a lot more than that. So it's very important, very important. There are a variety of ways which we can regulate pancreatic secretions. Generally speaking, there are 3 stimuli. The first of these is acetylcholine, which is going to be released as part of the cephalic phase of your gastric process. So you may have noticed that you can look at food and salivate. You look at food, you're like, I'm going to eat that soon. You're sitting at the table and somebody's bringing your plate of food to sit it down, and you can just feel your whole system preparing for the consumption there. Whenever you see food and you know you're going to eat it, you'll start to crank out acetylcholine, and that's going to stimulate for the release of these chemicals, just kind of getting everything ready for the digestive process. Next is cholecystokinin or CCK. Basically, when your chyme gets into the small intestine, if it contains fatty materials, the mucosa will pick this up, and cholecystokinin will be released. And that's going to cause a release of products from the gallbladder. You know, why? Why would this be done? Why would we release bile as a response to fatty materials in the small intestine? Pretty obvious. These are emulsifying agents. So the bile will help to emulsify the fats that you've just consumed and allow you to then absorb them. Again, we're going to be also releasing pancreatic lipase here. So we're going to emulsify these fats and then use pancreatic lipase to digest them and then absorb them into our intestinal system using our, what do you call them? Lacteals. Using our lacteals, which I probably should have shown you already, but we'll see how this pans out. And then, of course, there's secretin. Secretin is really important when you pick up acidity in the intestinal system here in the duodenum. That acidity needs to be dealt with immediately. So this is going to release secretin, and secretin causes the release of all these chemicals here, which contain bicarbonate to buffer the pH of the hydrochloric acid coming out of the small intestine, or coming out of the stomach, I should say. So the stomach's releases are very acidic, and when this happens, you release secretin, and that increases the release of your bile and what have you to help you buffer pH. Yeah, that'll do. Yeah, that'll do. Let's go here. So the small intestine. So in the small intestine, here's our lacteal that helps us absorb lipids, as I was saying previously. The small intestine is small in diameter. It's about 1 inch. Okay, about 1 inch in diameter. I'll give you an exact measure here. About 2.5 centimeters, but it's 18 feet long. So your intestines are super long. I always cracked up, man. When we did cat dissections back in the day, every now and again I'd see somebody cut the intestines out of a cat and then stretch them out, and it would go about like most of the way across a room. Like, you wouldn't believe how long these structures are. And the reason the small intestine is so long is because the early parts of the small intestine will be digesting all the foodstuffs that are there, and then the middle portions of the small intestine, towards the end I should say, are going to be absorbing the nutrients that are there, and then there's sort of a buffering layer at the end of the small intestine where we do a few other things, as I'll show you in just a second. So yeah, that'll do. So long, big organ, but small in diameter, so we call it the small intestine. So a variety of enzymes secreted by the pancreas, as I just described, are going to allow us to digest all of the major nutrients that we take in here. Bile is going to be there to help us to emulsify fats. All of this is true. What I really want to talk about on this slide are your villi and microvilli. Okay, your intestine here. Look at this slide over here. See all these villi? These are projections. All these projections. There's all these projections, especially here in the jejunum, which we'll talk about in just a second. But you have all these projections that are just sticking out into the lumen of the small intestine. Those projections are called villi. Okay, finger-like projections that are going to be sticking up into the lumen, and what they do is they increase the surface area that's found there to increase your capacity for the absorption of nutrients. And not only, this is very important, not only are there villi, but then the cells themselves have microvilli. And again, I've got a picture of that for you as well. So if that is a single villus, the microvilli are tiny little hair-like projections. Okay, tiny little hair-like projections that are going to stick up and off of these villi, and they give rise to what we call the brushy border. Probably have that on here somewhere. You got brushy border. Okay. The reason we call it the brushy border is because it has a furry, brush-like appearance. Okay. So not only do you have an intestine with a lumen, but that lumen has villi, and those villi are covered in itty-bitty, tiny, microscopic microvilli, which give the intestine, the small intestine in particular, just an astounding amount of surface area. An astounding amount. Your book would say that with the villi and microvilli, your intestine as a single individual would have enough surface area cellular-wise to cover an entire tennis court. So you have a massive amount of surface area. Why would you want all that surface area? Because the more surface area you have, the better you are at absorbing nutrients. All right, so amino acids, sugars, what have you, will be absorbed into capillaries. There's any fatty materials have to make their way in via the lacteals. That's true. All right, long story short, the small intestine is where digestion is finished and nutrients are absorbed. So we've been digesting and digesting and digesting both mechanically and chemically all throughout the whole time, but the majority of digestion happens in the small intestine, and that's where all of the absorption happens. I'm going to give you air quotes, all, and I'll tell you why that is in just a second. We're going to say all the absorption takes place in the small intestine. All right, sort of already showed you all this. Maybe I don't even need this slide. This is the way it goes building these lectures. But you can see that nice lacteal inside of there, which would be absorbing dietary fats. You can see all the capillaries inside of there. What I will talk about a little bit is this brush border and what are called the brushy border enzymes. So your brush border, the cell membrane there, has enzymes built into it that do not move into the lumen. They stay attached to the microvilli, and as materials are flowing through the small intestine, these brush border enzymes will be breaking them down as they go. Imagine an assembly line of materials running through, and you've got folks standing there, doing a certain job every time they see a certain product. That's what these brush border enzymes are doing. This is oftentimes considered contact digestion. Yeah. All right, I think that'll do. I just want to point out that this exists. You have these specialized enzymes that are hanging out in this brush border and helping you to digest certain things. These are brush border enzymes, and they are not moved through the system and destroyed. They hang out for prolonged periods of time on these brush border cells of this simple columnar epithelium and do their job there. Just pointing out that this exists. All right, and that takes us to this slide where I'm going to talk about the different parts of the small intestine, of which there are three. These are the duodenum, which is the very beginning, the jejunum, which is sort of the main middle bit, and then the big, long ileum at the end. Now, the duodenum is pretty short, only about 20-25 centimeters, and it's relatively stationary. There's not a lot happening there. What makes the duodenum kind of interesting from my perspective is that if you look down deep in the submucosa here, you have all of these what are called Brunner's glands, or what else do they call them? Duodenal glands. Duodenal glands or Brunner's glands. So when you're doing histology of the small intestine, what you want to look for if you're looking at the ileum or the duodenum or the jejunum, when you're doing duodenum, you're looking for Brunner's glands, okay? And what these Brunner's glands do is they produce a bicarb-rich mucosal solution that sort of coats the walls of the duodenum, so any acidic material moving through is going to be buffered by that acidity, or buffered, I should say, by that bicarbonate, and then that mucus layer is going to be there to protect the walls of the small intestine itself. Yeah, works like a charm. Then the 8-foot portion after, oftentimes called the jejunum, is going to be where all the major digestion and all the major absorption takes place. So where are we breaking down materials chemically for the most part? That's in the jejunum. Where are we absorbing nutrients for the most part? That's in the jejunum. Again, look at the crazy villi in the jejunum compared to the duodenum and the ileum. All these crazy long villi with their brush border enzymes. They're going to be absorbing massive quantities of nutrients and assisting in their breakdown. So it is in the jejunum that we break down and absorb the majority of materials. And then last but not least, the ileum. And what makes the ileum interesting are these Peyer's patches, which we've been talking about for weeks, I feel like. Peyer's patches being bits of lymphatic tissue that are monitoring for potential invaders, potential pathogens trying to make their way in from the large intestine. So your large intestine is just packed with bacterial interactions, And those bacteria don't need to get into the small intestine to be absorbed. Your body is in the small intestine, we are absorptive, so we don't want those bacteria getting from the large intestine into the small intestine. To help us make sure that's not happening, we have the ileum here with its Peyer's patches to monitor for potential pathogens and then instigate a mass release of materials, if you will, to wash it out if necessary. And again, think about this, 25 centimeters here, 8 foot there, 10 foot there. This is a big, long tube. It's massive. So here's my wife and daughter for scale. So my wife, all of this would fit in that little cavity there, okay? That little bitty critter. Yeah, that's how this works, man. So you got your esophagus coming down, liver, stomach, small intestines, to large intestine, and then out. Let's go here. Intestinal mobility. So your contractions of the small intestine serve a few functions. Mainly we're going to be mixing chyme up and sort of mixing the chyme with pancreatic juices and getting things stirred up together for good digestion to take place and to neutralize the acidity that's there. We're then going to churn the chyme in a special way that brings it into close contact with your brushy border for further digestion and then absorption through the villi that are there and microvilli. And then last but not least, the movements are going to be used to push waste products, if you will, out towards the large intestine. Now, in the realm of intestinal mobility, there are two types. The first is called segmentation, and the second is called peristalsis. Segmentation, you can imagine, is like if you have your small intestine here, you can imagine it kind of just squishing back and forth material. Squish, 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 squish. Just kind of squeezing as it goes and not pushing material down and through, but just sort of moving it around to keep a constantly fresh surface for the intestines. So imagine foodstuffs right in the center of this little ball of chyme here would not be getting any access to the surrounding villi. So then we're going to squish that in the other direction, so anything that was in the middle comes into contact with the villi and microvilli of the small intestine. So during segmentation, which takes a little time, this is all instigated by pacemaker action, segmentation is just going to be kind of squishing all this material back and forth, back and forth, back and forth, to make sure that we have the ability to absorb all the nutrients from this as is physically possible. Yeah, the purpose of segmentation is not to mix, the purpose of segmentation is to mix and churn, not to move material along. That is peristalsis. So once we are pretty satisfied that we've absorbed all the nutrients we can get, we'll run peristalsis and push that material down the line, all right? And what will happen is, like you imagine this big, long, small intestine tube, we'll kind of start a strong contraction, kind of milk it down, and start it here, strong contraction, kind of milk it down, strong contraction, kind of milk it down, strong contraction, kind of milk it down. That's good old-fashioned peristalsis. This is going to be slowly pushing material down the length of the small intestine and getting it into the large intestine to be further dealt with. Yeah. All right, I think that'll do. Speaking of the large intestine, here we go. So the large intestine is going to be broken down into a few parts. What we have here is the cecum, the ascending colon, the transverse colon, the descending colon, sigmoid colon, which is S-shaped. Sigmoid colon, you got to imagine this is going deep, forming a weird S curve, and then into a rectum. The rectum is like a storage area, and then there is an anal opening or an anal canal. All right, so let's run through and talk about it. Why is it the large intestine? Man, I'm going to forget something if I don't tell you now. See these lumps here, all these little weird lumps? They're called haustra, H-A-U, haustra, and that is how we break up the large intestines into these individual haustra. And we're going to talk more about that when we talk about haustral contractions. Okay, just had it on my mind, had to get it out. So what makes this the large intestine? It's actually a great deal shorter than is the small intestine. The large intestine is only about 5 feet long, but the trick is that it's much larger in diameter. So it's much larger in diameter than is the small intestine. That is what makes this large. And further in and amongst this, we have our vermiform appendix at the very base of the large intestine. We believe that the appendix might serve a variety of roles, but mostly revolving around bacterial activity. well, what the heck, let's just talk about it. So this may be an early warning system. So if we have potentially dangerous bacteria hanging out in the large intestine, the appendix may sequester those and help us absorb them so that we can pick up what they are and learn to deal with them. Or alternatively, another interesting nuance to this is that if we get sick and we have diarrhea and we free all the materials from our large intestine, that may wash out large portions of the bacteria that are hanging out in the large intestine, and the appendix might be there as a little storage vessel of those good bacteria so they can then reinvade the large intestine and set shop back up, if you will. All right, that'll do. Yeah, so our large intestines is packed with bacteria, trillions of bacterial cells. So what does the large intestine do for us? The large intestine isn't really an absorptive organ. It doesn't have transport protein carriers, so it's not really an absorptive organ. What it does is it pulls out water. Once material gets into the cecum of the large intestine, it's going to be feces, okay? And you're pulling the water out of that slowly. So you can imagine the fluid in the cecum is quite fluid and watery, and you're going to slowly move that up and through the transverse colon, eventually down the descending colon, and we're slowly congealing this into a more solid mass of feces, and eventually it's going to wind up in the rectum as literal solid feces, and then you'll have a choice to make about when you're going to eliminate that from the body. So the goal of the large intestine is to absorb water and keep you from becoming dehydrated. You probably realize if you get diarrhea that the problem is you might become dehydrated, which is scary, but the main, no pun intended, the main goal here is to absorb fluids. Now, there is some evidence that we might be able to absorb B complex and K vitamins from the large intestine. Basically, all the bacteria that are hanging out in the large intestine are breaking down indigestible materials. Like, you can't digest these, but the bacteria hanging out in there have the enzymes that will allow them to do so. So these bacteria are breaking those things down like crazy, doing their thing, and that's releasing K and B vitamins in some cases. And there is some evidence that as we are pulling water back into the bloodstream through the large intestine, we may inadvertently pull some B and K complex vitamins into the bloodstream as well, as a byproduct of bacterial activity. Yeah, all right, good, let's go here. So in the realm of gastric motility of the large intestine, or of large intestinal motility, I should say, we have haustral contractions. These are very slow and simple things. You got these haustra, these are the enlarged little lumpy bits here on the large intestine. And what will happen is you'll squeeze one off, and then you'll squeeze off another one, and then you'll squeeze off another one, basically in 30-minute cycles. And you're just slowly transporting materials around the large intestine. It's a slow process, not a big deal, it just happens. But then about 3 times a day, you'll have what's called a mass movement. So imagine you're sitting around doing the things that you do, and suddenly you feel this crazy cramping across your intestinal tract. It's like, oh, man, oh, what is that? And normally you can feel this in the transverse colon. It'll start on the right, it'll go cross to the left, and you're like, oh, whew, that was rough. All right, what's happening there in most cases is right after you eat, or right around when you're gonna eat, and your intestine is making room, okay? It's like, wow, there might be more stuff a-coming. We better get this out to the rectum. So it's gonna move all that stuff real quick. This crazy big, like a big cramp, all the way across the intestine, pushing that stuff down towards the rectum to assist in ridding the body of those wastes. When you got more stuff a-coming, you gotta make room for it. All right, let's see, what do we wanna say here? Okay, feel free to read this. I'm just going to tell you what happens. What will happen is as follows. When you build feces and you've got a solid lump inside of there and it's ready to move, what will happen is it'll fill the rectum. And when the rectum fills, this is, by the way, this is exactly like urination. Same exact process happens in the bladder for urination. So when the rectum fills, that's going to send a message up to the brain, and the brain will then respond by sending a message back down that causes the rectum to kind of contract a little bit, and it will open one of the 2 anal sphincters. So there are 2 anal sphincters, an internal anal sphincter and an external anal sphincter. This is important. The internal anal sphincter is smooth muscle, which means autonomic control, whereas the external anal sphincter is skeletal muscle, which means conscious control. So when the rectum fills, it causes a little contraction, and that opens up the internal anal sphincter, and it's going to push feces against the external anal sphincter. And what that does is it tells you, it's like, ooh, I should probably go to a bathroom. All right, just saying, hey, you could go to the bathroom right now, or you could not. You have a conscious decision to make. You can voluntarily control that external anal sphincter and keep it closed, or alternatively, you can relax it and allow feces to leave, typically by this Valsalva maneuver that we've talked about previously. I will explain my son's process to you for kicks and giggles here, I suppose. So my son, the youngest, is 2, and he is potty trained like a champ. You wouldn't believe this guy. He's amazing. But I shouldn't do this. But he'll sit there and he'll go, 2, 1, go. Like this. You know, you take a deep breath and you squeeze your abdominal muscles. That's Valsalva maneuver, and it's going to help us to push materials out of the intestines and make room for more later. All right, perfect. Let's go here. Water in the digestive system. So your digestive tract receives about 9 liters of water per day, and virtually all of it gets reabsorbed. Now, it is possible, hang on, let me go back further to make the point here. You have to reabsorb that water or you're going to die of dehydration. Okay, you got to get that water back in. Dehydration is a real issue here. So we only leave out about 0.2 liters of water in our feces output in a day. So very little is lost in the grand scheme of things. Now, it can be lost at much greater rates when we have diarrhea. So diarrhea means to flow through. So materials come in and materials flow out. They flow right on through without being adjusted by the digestive system. That's good old-fashioned diarrhea. It's very important. Given certain situations, like when we have an infection, or if we have we consume foods that are poisoned in some fashion, like food poisoning, a whole variety of things can lead to diarrhea and blowing materials through our large intestine without absorbing fluids back. This is dangerous because we can dehydrate. And then alternatively, the flip side of this is constipation. So when you hold on to feces for too long, if you let it sit in the intestine too long, more and more fluid gets pulled out, and man, it turns out like little rocks. And passing little rocks is no fun for anybody, so you want to avoid that. So whenever you get the feels, you want to let stuff out, all right? Convincing your kids, man, let me tell you, it's not an easy task. And then, of course, there's feces. So your large intestine takes about 12 to 24 hours to reduce the residue of food into feces. Feces are about 3/4 water, so it's mostly water, and then the rest is bacteria and dietary fiber and any other indigestible things that are found there. The smell, the stink of feces, I should say, is a result of the gases produced by the bacteria that are there. Those bacteria, again, have all sorts of crazy enzymes, so they're capable of breaking down things like cellulose or any other indigestible materials that you can't break down. And as the bacteria break these down, they release gases. Part of the process, okay? And further, the activity of these bacteria breaking down things like bilirubin, as I said previously, gives off kind of a weird yellowy orangey pigment, and the oxidation of the iron therein gives it feces this brown color. And then last but not least, sometimes feces have a green color. This can be a side effect of having a lot of chlorophyll in the diet, like eating a bunch of salads, or if your feces are moving very quickly, that could be bile in the fecal materials, and that's just a side effect of it moving through really fast and not having time to absorb the fats that are there. So it's emulsifying agents. And then for kicks and giggles, I'll show you this. These are dinosaur feces. They're called coprolites, and they're basically rocks at this stage with crazy colors. You can find these all over the internet. It's kind of a neat thing. There were a lot of dinosaurs out there, and that means they made a lot of feces. And this is actually a knife handle made out of coprolite. I think it'd be really funny to have a whole cutlery set, so when people come over to my house, you could be eating, and then you could slowly explain to them what the knife handle is that they're using is made of. I think that would be hilarious. Anyway, all right, some digestive disorders, and then we're going to call it a day. So I'm not going to go into a lot of detail on these, don't have time. Hepatitis is any inflammation of the liver. There are 3 forms, A, B, and C, and all of these are treatable these days. Previously, hepatitis C was non-treatable, but now we're getting pretty dadgum good at giving you a shot or two and getting rid of hepatitis C. Works like a charm. I think it's even being covered by insurance these days, which is fantastic. So that's great. Hepatitis is on the way out as a result of this. Cirrhosis of the liver is when the liver becomes fatty and then scars over. This is oftentimes a side effect of too much alcohol intake. So alcohol is actually an incredibly high energy compound. So when you drink copious quantities of alcohol, that's a lot of energy that the body has to deal with, and it deals with it by making a lot of fat, and that fat gets stored in the liver, and over time that leads to the liver losing function and scarring over. That's cirrhosis. And then, of course, there's heartburn. So if your gastroesophageal sphincter is not working correctly to close off the stomach, when the stomach is churning around doing what the stomach does, some of that acidic kind can move up into the esophagus, and the esophagus has no defense against the crazy acidity and enzymes of the stomach, so it begins to erode away at the esophagus and leads to pretty crazy pain and suffering, if you will. It hurts real bad. Normally we just treat this with like things like Rolaids or other materials. So antacids, like a Rolaids tablet or something like that, those are bicarbonate. Same thing your pancreas releases. So we use those to relieve the pain in the esophagus. Diarrhea, we've sort of already talked about, can lead to dehydration. Constipation, we've sort of already talked about. And when you are constipated and your feces become incredibly hard, it can cause damage to the anal opening while you are trying to relieve yourself, and that can lead to things like hemorrhoids. So hemorrhoids are where the blood vessels around the anal opening get really swollen and painful, not an ideal situation, not a comfortable feeling. There are also diverticulosis. Diverticulosis is where you have mucosal, call it, hernias. Hernias of the mucosa pushing their way through the muscularis and forming these weird blinded ended sacs called diverticuli. Again, this is diverticulitis or diverticulosis. And these blind-ended sacs can get bacteria in there, and they start chowing down, and they swell, and they hurt, and they'll pop internally. They'll pop back open and go back in, and it's not a good feeling. It's just a really uncomfortable feeling, and normally this is descending colon territory for the most part. So we're on the descending colon. Do I have that on here someplace? Yeah, good. And then last but not least, polyps and cancer. So when you are aging, get around 40, you got to go in and have your GI tract sort of inspected with a camera. They go in and they inflate your whole large intestine, and they go in with this camera through the back end and look for polyps. That's what that is there. That's a polyp. And these can potentially be cancerous. So what they do is they loop this wire around it, burn it off, and cauterize the wound, and remove them as we go. It's not really a big deal these days. It's pretty common practice. And last but not least here, so I threw on here some good breakdowns of the enzymes, what they do and where they're found and all that fun stuff. I would not delve too deeply into this side of things. I've already told you everything I want to tell you. I just found these and I thought they were useful, so I left them on there in case I want to use them at some stage later on. So that's going to be that, folks. I think that is the extent of it. That's the digestive system. So I hope that's a benefit to you. Get on it. I'll be building a quiz on this before you know it. Thanks.